Let's do an example of evaluating an integral with a more complicated function. You can find a bunch more practice exercises like this one on Mooculus. So the more complicated integral that we want to evaluate is the integral from 0 to 5. So our lower limit is 0, our upper limit is 5. The function that we're working through is x times e to the x squared plus 2. And then we have dx. So I want to evaluate this integral using the fundamental theorem. The fundamental theorem tells us that the easiest way to evaluate this integral is to find an antiderivative for the function. So let's go ahead and guess some antiderivatives and see if we can find one. All right, so let's guess some antiderivatives. The textbook has some ideas when we're talking about some of the different templates, and I have x times e to the something. So I've seen some problems like this before. I'm thinking about what the antiderivative might be, and so maybe my first guess is x times e to the 3x squared plus 2 for my antiderivative. Well, let's check and find out what's going on. So I take the derivative of this function. I take the derivative of the first thing, that's 1, times the second thing, e to the 3x squared plus 2, plus, using the product rule, x times the derivative of this, well, that's e to the 3x squared plus 2 times 6x. So I'm looking at this derivative and I'm really feeling a little bit depressed, right? Because here I have this e to the 3x squared plus 2, and when I've done this before, I've thought about maybe subtracting that off, so that would be possible. But over here I have x times e to the 3x squared plus 2 times another 6x, so I'm really increasing the power on x here. So probably this is not a great idea for my antiderivative. But thankfully, I have another guess that is usually made in this case. Right? Let's just guess e to the 3x squared plus 2 for my f of x. All right, well, then we check to see whether this is a derivative, and I think probably not, because I'm probably going to at least have to adjust some coefficient. Right? But I take the derivative, and now I get the derivative of e to the 3x squared plus 2 is e to the 3x squared plus 2 times, using the chain rule, the derivative of the inside function, which is 6x in this case. So simplifying this, I get 6x e to the 3x squared plus 2. And now I'm feeling way better than I was before, because this looks a lot like the function that I have, except I just have a coefficient of 6 on the front. So my last guess will be f of x is equal to 1/6 e to the 3x squared plus 2. And when I check this derivative, f prime of x is equal to, well, 1/6 times e to the 3x squared plus 2 times the derivative of the inside function 6x. And in fact, this 1/6 and this 6 cancel, so I just have x e to the 3x squared plus 2. Great job. Now that we have our antiderivative, let's go ahead and evaluate this integral. All right, so I got my antiderivative. This was the one that we used here. 1/6 e times 3e to the power 3x squared plus 2. And so the fundamental theorem of calculus says that the integral from 0 to 5 of x times e to the 3x squared plus 2 dx is my antiderivative evaluated at 0 and at 5, and I subtract those two things. So what did I get? Well, my antiderivative from here, 1/6 e to the 3x squared plus 2, and I'm going to evaluate this from 0 to 5. Well, what do I get? First, I evaluate at 5, so that's 1/6 times e 3 times 5 squared plus 2. And then I evaluate at 0, and I subtract these. So I have 1/6 e 3 times 0 squared plus 2. So simplifying this, I can factor out the 1/6 because I have that in both terms. So this is e to the 3 times 25 plus 2. Minus e to the, well, 0 squared is 0, and 3 times 0 is 0, so this is just e squared. And so simplifying again, 1/6, 3 times 25 is 75, so 75 plus 2 is 77. I get e to the 77 minus e to the 2. And if I wanted to approximate this answer, I could certainly put it in my calculator and find an approximate value, but if I was doing the problem on Mooculus, probably they want me to enter an exact answer, and so I would type in this thing just like that. This might have seemed like a whole lot of work for nothing, especially if you have evaluated integrals before using different techniques. In some sense, you're right. Next week, when we talk about techniques of integration, we'll have an easier way to think about this problem. It'll be called U substitution. Until then, all we have in our toolbox is just guessing the antiderivative, so that's the strategy that we want you to use this week. Good luck, and make sure you practice some problems like these.